Alrighty, hello and welcome to video set 2, Electric Boogaloo. So we're now going to be working with magnetic fields and magnetism. So if you thought electricity was fun, just you wait. More particularly, we are looking at motion in a magnetic field, so particularly with what happens when you have a charged particle, that's our electrons and protons, moving through a magnetic field. And here is our main formula. So the force that acts on a charged particle moving through a magnetic field is equal to the magnitude of its charge times its velocity, these are vectors by the way, times the strength of the magnetic field times the sine of the angle between the velocity and the magnetic field. Sounds like a mouthful, but it is a little bit easier in practice. So let's get right into a problem here. For those of you following along at home, we're on page 649, problem number 5 in chapter 19, which is, you guessed it, magnetism. So I'll read the first part out loud. A laboratory electromagnet, a magnet, produces a magnetic field of magnitude 1.5 teslas, that's the T. A proton moves through this field with a speed of 6 times 10 to the 6th meters per second. Here's our strength of our magnetic field, that's a vector. Here is our velocity of our proton. We just wrote those out at the beginning. So now, find the magnitude of the maximum magnetic force that could be exerted on the proton. So the maximum magnetic force is going to be the maximum value of our maximum magnetic force equation. So the magnetic force is equal to the velocity of the proton times the magnitude of its charge times the magnitude of the magnetic field times the sine of the angle between them. A really quick aside, for those of you who are familiar with vectors, this part right here should look very similar to the cross product of the velocity and the magnetic field, because the cross product will give you the magnitude of the cross product vector is the product of the magnitudes times the sine of the angle between them, and so we have that same thing there. So force is really the magnitude of the charge times the cross product of the velocity vector times the magnetic field vector, but we don't want to do cross products because those are gross and annoying, so we leave it like this. So just going into this part right here, and we're going to tackle part A because that's what the problem says. If we want to maximize this, we already know the charge of the proton. That is a constant. You won't need to memorize it on any kind of test, but it is 1.6 times 10 to the negative 19th coulombs. We know that. We can't change it. And we also know our velocity, that's given. We also know the strength of the magnetic field, that is also given. The one thing we aren't given is the sine of theta, and this is where the maximizing part comes in. So if we want to maximize the force that a magnetic field applies onto a moving charged object, then the way to do that is to have the velocity be perpendicular to the magnetic field. That is a basic tenet of our magnetism work, that the velocity, if it's perpendicular to the magnetic field, that will maximize the force. We also know that because if they're perpendicular, then the sine of the angle between them will be equal to sine of 90 degrees, which will be 1, and 1 is the maximum of the value of the sine function. So 90 degrees is the best angle that you could plug into the sine function to get 1, so 90 degrees is what will maximize that. So once we know that that is our maximum, we now just plug our values in. So we plug in our charge for a proton, which is 1.6 times 10 to the negative 19th coulombs. We plug in our velocity, given to us as 6 times 10 to the 6th. If I could write, that would be nice. And then 1.5 teslas. And then sine of theta. We said the best sine of theta, the maximum force, is when that is equal to 1, so we can just ignore that actually. And so that will yield a result of 1.44 times 10 to the negative 12 newtons. So this right here is our maximum force. It is only the magnitude of the force. Keep in mind, we don't yet know the direction of it. If we had that, then we would need the direction of the velocity, the direction of the magnetic field, and then you could do some mental gymnastics and a little right-hand rule to figure out the direction of the force. But for now, that's the magnitude of the force. That's the solution to part A. So now we get into part B. Part B, we need to find the magnitude of the maximum acceleration of the proton. So to do this, if you're thinking force and acceleration, you should immediately be thinking of Newton's second law. So that says that the summation of force acting upon an object, in this case our proton, summation of force on our proton, is equal to the mass of the proton times the net acceleration of the proton. And all of the summations and nets and things like that, that won't come into play because we only have one force acting on it. So really, the force from the magnetic field is equal to the mass of the proton times its acceleration. So that's a little bit simpler because we only have one force to worry about that's acting on the proton. So let's rewrite this to get acceleration by itself, because that's what we're looking for. Acceleration equals force over our mass of the proton. This is a relationship that if you didn't already have down in your brain, you will want it. We're going to use it later in this problem, and it will be incredibly useful for just about every physics work problem that you're going to encounter. So the maximum acceleration, it says maximum acceleration, that will occur when we have the maximum force. Our mass is never going to change, so the maximum acceleration occurs when we have our maximum force. And just like magic, we already found our maximum force, so it is quite easy to just plug in our acceleration. We plug in our maximum force of 1.44 times 10 to the negative 12 newtons, and then we plug in our mass of a proton, which is 1.67 times 10 to the negative 27 kilograms, and that gives us a final answer of 8.62 times 10 to the positive 14th, so that's a really large number right there. Meters per second squared is our acceleration unit. So, something to keep in mind is even though this force was 10 to the negative 12, it's very small because a proton's mass is so much ridiculously smaller that the acceleration ends up being really quite large. So that is something to keep in mind. And you might also think, well, 1.5 Teslas is not a very large number. In fact, 1 Tesla is a very, very large number for a magnetic field. Earth's magnetic field is less than 1,000th of that value. So just some things to keep in mind. Part C. Would the field exert the same magnetic force on an electron moving through the field with the same speed? So, force has two components. It has magnitude and direction. So we're going to see which of these are the same. So, the magnitude. The magnitude of the force, we have the same velocity, the same magnetic field. We're going to use the same sine of theta because we want to still maximize it. So we have the same sine of theta, same magnitude of the magnetic field, same velocity. The magnitude of the charge is the same because electrons and protons both have the same magnitude of their charge. Electron is just negative. But the negative doesn't affect the magnitude, so the magnitude is the same. Good to know. The negative, however, will affect the direction. The electron will experience a force in the opposite direction of the proton because its charge is negative, so its force will be negative. And in physics, a negative force means it's in the opposite direction. So the direction is different. So the short answer is no, it will not be the same because the direction is different. And the direction is different because electron charge is not equal to, is the opposite of the proton charge. So you can think of it as they won't be the same, but they will be equal in magnitude, but opposite in direction. That would be a more detailed way to think about it. And let's squeeze on D in here. Will the electron undergo the same acceleration? And explain. So, acceleration, I told you we'd come back to it. Force divided by mass. We already know that the forces are in opposite directions, so we know right away that the accelerations are also going to be in opposite directions. So right away, we know that the answer is going to be no in some way, shape, or form. So we'll start by saying no because opposite directions. But also, acceleration is force divided by mass. Electrons and protons have hugely different masses. An electron's mass is less than 1/1000th that of a proton. So if the mass is much smaller than a proton's mass, then the acceleration of an electron, because they will undergo the same magnitude of a force, the electron will experience a much larger acceleration. So for the accelerations, not only are they in opposite directions, but they are also hugely different magnitudes. Hugely different magnitudes. And that's, again, because of the different masses of a proton and an electron. Different magnitudes, if I can spell. Alright, awesome. So that gave us two more plugging and chugging type questions and two a little bit more conceptual questions. We got to use our fun formula over here. We showed that it is connected to the cross product of vectors, and you will notice that becomes more important as you go further into magnetism. So I hope you learned something, cleared some confusion, or maybe just had a little bit of fun. I won't judge. See you next time.